Hi, I'm Via Kelly, and my presentation is on power systems in hybrid electric vehicle drivetrains. I'll be primarily drawing from the paper Unified Modeling of Hybrid Electric Vehicle Drivetrains by Rizzoni, Guzella, and Baumann in 1999. To get things started off, I'm going to talk about why it is I'm interested in this topic. So, I chose this topic and I'm interested in this particular topic because when I got my first car, it was an old car. It's a 2002 Nissan Sentra, and it has a absolute litany of problems with it. And of course, that means it's not very cheap to fix. So I started taking it upon myself to fix it. And from that point forward, I kind of caught the tuner bug, so to speak. And I've been interested in the design and engineering around vehicles ever since because of that, because I enjoy repairing them so much, to the point that one thing I want to do is actually modify my car. I'd like to make it into a hybrid vehicle eventually, and that means altering the drivetrain, installing an electric motor, um, and designing basically replacement systems that would run in parallel to the existing mechanical systems for the car. But what exactly is a drivetrain anyway? We have an idea of it basically because it's right there in the name. It makes your car drive. But there's not really, as far as I know, it's not really common knowledge to understand what exactly it's doing. Basically, what a drivetrain does is it converts the power from the engine into power to move the wheels in the car and therefore move the car itself. In a traditional gas vehicle, the only way this happens is through internal combustion that generates mechanical energy that's transferred through the camshaft and through the flywheel and then into the transmission through the transmission gears, and then the transmission gears put that power into the drivetrain to rotate the wheels. So in a standard gas vehicle, we only have one type of power essentially that's working, and that is the power from the internal combustion engine generating torque. In a hybrid vehicle, we have an entire suite of different types of energy being used. And I'm going to talk about that a little bit on this presentation. So an example of this would be in a fully gas-powered vehicle like, say, a 2002 Sentra, power is transferred from the motor to the drivetrain by the transmission, which is, in ideal circumstances, using the gear with optimal characteristics for delivering that level of power. So if you need more power, you shift to a higher gear. If you need more speed, you'll shift to a lower gear because it'll be more efficient at delivering the lower amounts of power you're generating. In a fully electric vehicle, sometimes you don't even need a transmission because instead of shifting gears, you can just change the phase that a multi-phase electric motor is using. Now, there's an advantage to that. There's less clunky parts. It's basically just the motor. And depending on the type of electric vehicle you have, it may not even have a drivetrain. Teslas don't, hence why they tend to be smaller. But this leads to a bunch of drawbacks, like the inability to transfer mechanical energy without converting it to electrical energy first. And these drawbacks are the reason why Teslas tend to be poorly designed. So how do we get around this for hybrids? Because we're using both types of systems. In a hybrid electric vehicle, both systems are present, and we need to figure out how we can transfer energy and how we can design a drivetrain that accepts the transfer of that energy. We can use either mechanical or electrical power to power the vehicle, but in the end, we always have to convert it into mechanical energy, because if we don't, then what happens is that we're not converting it to energy that can rotate the wheels. So each type of energy we can use for this is part of a specific energy domain. And in the paper I'm presenting on, is this flowchart is directly from that paper. As you can see, in a traditional combustion engine, we start with energy from the chemical domain, which is the fuel and air mixture. And then the combustion of that generates heat. It causes the flow of heat. That process is irreversible because of entropy. And as a result of that process, we gain mechanical energy because of the pistons in the engine and the camshaft. The difference between there's a very different feature here with electromechanical behaviors. Using your car's alternator, you can always convert mechanical energy back into electrical energy. And the same thing is the case with, for example, regenerative brakes. And you can always convert electrical energy to mechanical energy with an electric motor. And you can usually convert chemical energy into electrical energy. For example, with a fuel cell, or technically a battery is actually this process. And electrical energy can be converted back into the chemical energy domain through charging of a battery. So we have basically a basic idea of how this happens. There's only one of these processes that is irreversible, which is the internal combustion process. We can also change which domain the energy is in. That's what in the paper they call an interdomain energy transfer. Or we can change it to the same type of energy, but operating in a different part of the vehicle, or what they called an intradomain transfer. So an example of an intradomain transfer is mechanical energy going from the flywheel into the transmission, or going from the drivetrain into the differentials. The mechanical energy from the engine is moving, it is being transferred. It's no longer in the same place, but it hasn't changed away from being mechanical. An example of an intradomain change would be, as I said, using the car's alternator to charge a battery. What happens is that it goes from a mechanical energy, the spinning of the wheels, and the rotation of the motor pulleys, to electrical energy, and then the electrical energy becomes chemical energy when it charges the battery. So we have also storage systems, which I will talk about later, but they can, with varying degrees of success, store this energy so that we can use it at another time. So ideally, we want to manage the energy workflow in a way that maximizes two variables: the efficiency of the vehicle for the first variable, and the total power for the second variable. Now, the efficiency is represented by the equation I have here on screen. Basically, it's the ratio of the output work to the input work, or E minus the ratio of the work lost to the input work, where E is the peak intrinsic energy efficiency of the conversion process. It's essentially the proportion of energy lost by converting it, while here we have our efficiency eta is the total efficiency of the drivetrain. Now, how do we maximize this? Well, we need to build a unified theory, and that's what they tried to do in this paper. We need a way to compare the efficiencies of different parts, even if they're not from the same energy domain. So they categorize them in this paper as essentially different categories of variable. There's an effect variable and a flow variable. So in the case of mechanical energy, the effect variable is force or torque, and the flow variable is translational or angular velocity, which makes sense because what we want is an effect that's torque, but the velocity itself is what allows us to have torque in the first place. For electrical, we've got voltage and current, which are obviously going to be very familiar. Voltage is our potential, and current is the flow of electrons from one place to another. And for our chemical, we have our lower heating value and our mass flow rate, because the amount of chemicals going through the system are what's going to allow us to continue engaging in combustion, for example. What's not listed on the table here is there's also a state variable for heat, which is heat. Q is the flow variable. In other words, essentially the change of energy by heat. And the state variable is temperature. So for storage, we also have a similar thing going on. We have a state variable, but our state variables are different and our storage variables are different. So for mechanical energy, our state variable is going to be translational or angular velocity. And for electrical energy, it's going to be voltage. For chemical, it's going to be the lower heating value. And our storage variable for mechanical energy is going to be momentum, because the conservation of momentum means that we are able to store energy using momentum. For our storage variable for electricity, it's going to be charge. What we don't have is a storage variable for heat. We have a storage variable for chemical energy, which is just the mass of whatever chemical we're using in that case. But there's no real feasible way to store heat for a long period of time. So here's some general equations and some graphs that have to do with this. Once I skipped over a lot of the intense math that they've done here to derive these equations, but the general form of the equation which describes the work output is going to be the efficiency as a function of the flow variable times the work input, which makes sense when you think about it, because the efficiency is going to depend on what kinds of energy are coming in and out and how efficient those processes are. And as we know, the efficiency of any heat engine is equal, or any engine of any kind for that matter, is equal to the ratio of how much energy we get for how much we put in. And we also have a general equation for the energy stored, which is going to be just the integral from 0 to t of the storage variable times, the state variable times the flow variable. And the reason for that is, of course, because the state variable times the flow variable is essentially going to be the change in the storage. And we know from calculus that if you take the integral of a infinitesimal rate of change, you get the original function. Now, of course, this doesn't account for any constants of integration, but in that case, the constant of integration would be just the energy that we've already stored previously. So that's a known value that we can consider. As for the graphs, what you'll see here is this is looking at the comparison of the model to actual engine data. So what we're seeing here in the upper right graph is we are seeing it compared against a conventional fuel-based heat engine. So we're seeing that the mean effective pressure increases with the actual pressure, internal pressure of the cylinders, and we can see that the mean piston speed is going to increase with the lower fuel heating enthalpy. So basically what that means is what we expect for heat engines, that we are going to have a much more powerful engine if we have a higher pressure ratio and we have more fuel available. The other graph is the same model applied to a 83 kilowatt induction engine, or induction motor actually. And so basically what this is telling us is that we have a higher pressure in the motors, a higher pressure in the rotors of the motor associated with the piston speed. which is also more or less what we expect to see. But it does show that the model is producing a result that is consistent with what you would expect to see. So it's more or less like a sanity check. You can tell that the model isn't making claims that are particularly outlandish here. So let's take a look at the case study they do in the paper. What they did is they decided to mathematically model an SUV. And this SUV was going to be a hybrid that they were going to try to maximize the useful characteristics of and increase the fuel efficiency of by using the general equations that they had established. And so the reason why they chose an SUV is because they have a large towing capacity and they have four-wheel drive capabilities. And these are both things that are often difficult for hybrids and electric vehicles to pull off because they require a lot of power in a short amount of time. You can see here I've included the block diagram of the vehicle that they're simulating here and how it's transferring and how it has a parallel hybrid and internal combustion, a parallel electric and internal combustion system, this is why it's called a parallel hybrid. So they want to hybridize SUVs here because SUVs don't have very good fuel efficiency at all. And so making them hybrids is one way to increase their fuel efficiency, but the trade-off that most buyers would be worried about is, are they still as powerful? So using their model, what they found is that the most efficient option would be a 80 kilowatt diesel internal combustion engine and a 50 kilowatt three-phase electric motor. So what they found is that they got a 41% increase in efficiency when they combined it compared to a standard SUV. And they also found that it was still able to maintain its 1,000-pound towing capacity without having to sacrifice that efficiency. The design was so that it would be able to maintain that towing capacity on a 6% grade indefinitely and still have the regular acceleration characteristics of a conventional SUV. Because of the smaller engine size, what they found is the engine's top speed is lower than a conventional SUV, but that is not very relevant to most users who will not be driving at a top speed, even on highways. And the vehicle's mass was increased by 100 kilograms. But this other graph in the lower right corner shows that the internal combustion engine at lower ranges showed massive boosts to efficiency, and at higher ranges, an even more massive boost to efficiency. In middle ranges, it was slightly less efficient than a conventional SUV. However, most drivers ideally should not be using it in those mid-range areas anyway if they're using it as either a towing vehicle or a regular driving vehicle. It should be generally used at the low range, with occasionally being used for towing, in which case it would be in the most efficient state. To quote their paper, if the required power exceeded the limitations of the internal combustion engine, the electric motor would turn on. And at suitable operating points, the supervisor reloaded the batteries such that the charge of the batteries was the same at the start of each cycle. What this did is it prevented the electric motor from ever running out of power, and it also prevented the internal combustion engine from ever pushing itself to the point where it could cause damage to the vehicle or where it could get a loss of efficiency from operating in a non-ideal environment. One thing that they did note is that there would have to be further work because they didn't account for emissions in the model, and they didn't account for certain factors such as drivability, what control algorithm should be used to decide when the internal combustion engine is used and when the electric motor is used, what pollutants and emissions it might produce, and so the results have to be treated with a degree of caution. But they do show a great potential for being able to model hybrid vehicles. By comparing the designs of conventional and parallel hybrid SUVs using the public data for the conventional vehicle as a comparison point, they showed that the use of the modeling technique and simulation tool was workable. And that is my conclusion. Thank you for watching.